All right, and welcome back to the second day of the hands-on machine learning course. I hope you had a nice time yesterday. And today we will continue with some more advanced topics. So yesterday we discussed the logistic regression, linear regression, and k-means clustering. Today, we will do it slightly different. We will start by looking at model quality and selection, which is, I think, a very important topic. And after each session, again, we have exercises, but today we will work on one larger project where in theory, you can do whatever you want. On the GitHub, I've put some, let's say, tips for you if you are a little bit lost on what to do. And basically, I think we will work in blocks of, again, 1 hour or something, or a little bit longer. And then we will introduce a new topic. And then after the new topic, you can try to implement that again during the project, and then we will close off with the ensemble methods and again some additional project work. So that's the idea for today, and let's get started with the model quality and selection. Again, if you have some questions, please put them in the chat or unmute yourself. So I think really the when I was talking about the art of machine learning in the first day, I think this is where that bit is, where you need to start balancing, you know, the the quality of your models, see how you can improve them, whether they are good enough, and how to actually test them properly. Because I think now what we have done in the first day, you were basically able to just train the model and maybe already a little bit testing with the validation set approach that we already a little bit introduced during the exercises. However, if I now would ask you, are you confident that the model that you built yesterday is going to work in practice? I don't know how confident you will feel with that. So I'm not sure whether you would put any money on your model, whether it's going to work, for example, better than just a coin flip. And that's what all this what this bit of theory is all about. So how to assess whether your model is actually doing better than just random guessing, but also just assessing how good your model is doing in general. So we are really talking about looking at quality of fit by measuring the accuracy. And this is basically, we need to answer the question, how close are the predicted values that basically come out of our model, how close are they actually to the actual y value. So as you can see here, we will only talk here about supervised learning, because for unsupervised learning, we don't have any actuals to compare our predictions to. For linear regression, we have already discussed a good method to test whether your model works fine, at least for testing, for training purposes, and that was the R-squared. Just to recap quickly, the R-squared was looking at the residual sum of squares and the total sum of squares. Residual sum of squares, you could calculate that by looking at your prediction, which is this blue line, and then the distance or the error compared to the actual data point. So here you can see the green line is basically the error. To get the residual sum of squares, you need to square that distance or that error and also sum that for all the data points that you have. That will give you this one. Total sum of squares looks at the difference from each data point towards the mean, and then sum that. And this gives you the R-squared, which is something, for at least for training, something between 0 and 1, and you want to get that one as close as possible to 1. However, there are actually multiple ways to multiple KPIs that you can use for testing the performance of your model. So what you could also just look at is just the residual sum of squares without even doing something else. So that's just looking at the squared error of your model. Another commonly used one is the mean squared error. So you can see it's very close to the residual sum of squares, because In both cases, you take the sum of all data points, and then you compare the actual y value with the predicted value. So there are two ways that you can basically denote predicted value. That's either with this y hat, or you could say this function f hat, which is basically your model, and where you input the features of the ith observation. So these two notations are basically the same thing. Again, with the mean squared error, this is again within the parentheses is the error. You square it, sum it. The main difference with it with the residual sum of squares is that you take an average. Furthermore, you could also look at, for example, the mean absolute error. Again, very similar to the mean squared error. Main difference here is that we don't take the square. We just take the absolute value of the error and then take the average of all those errors. Then the mean absolute percentage error is even one step further, because in that case we want to look at the mean absolute percentage error, which basically means you have your error again, y minus your, so the actual minus the prediction, but you divide by the actual. This gives you, let's say, the percentage error compared to the observation itself. In certain cases, that might be a lot more useful, because the issue with the mean absolute error is that it depends on the unit of measurement on your y, or the magnitude of y. So mean absolute error will by definition be large, probably be very larger, I mean, when the magnitude of y is larger, and vice versa. If the magnitude of y is smaller, then the mean absolute error will also be smaller in general. So in that case, in certain cases, you might get more out of it when you just look at the percentage error for each observation, and again take a mean and times 100%. All these work really fine for regression problems. So I think all of these you could use and should use probably, and then based on your context you can pick one or multiple, but in general I would always recommend to just calculate them all and compare them alongside. However, the question is, can we actually use these KPIs also for classification? Well, in general it's not that easy, because classification is just, for example, if you just have two labels, you have either a 1 or a 0. However, you could use, in theory, the mean absolute error for classification. But still, if you look at it, it's kind of weird, because if you just predict labels, so either 0 or 1, so y is either 0 or 1, or the function is 0 or 1, so the error can either be 0 or 1. And if you sum that, you're basically just summing the number of mistakes you made and then divided by the number of data points. So you would get a percentage of correctly classified instances or observations, which would work. Which would work, but there are actually better ways to do this for classification. I see here a question: how do you know which is the best fit for our data set? So in the case of regression, I would just always use all of them. That's basically the best way to compare it, and you should just, or if you have different models, compare each of the KPIs independently and see if all of them were improved, or that just a subset was improved. For classification, we will see that picking the right KPIs is more difficult, because I think there you really need to make a selection. For regression, I think you can typically just use all of them. Even there are more, but these are the commonly used ones. So for classification, we have something called the confusion matrix. And it's actually, if this is the first time you see a confusion matrix, I think it will be really confusing. So the confusion matrix looks like this. You have rows and columns, and on the rows, you are going to put the labels of the actual data. So with negative, we typically mean the labels that are, for example, 0, and positive are the ones that are 1. We can do the same thing for the predicted labels, and we put those on the columns. So you get your negative predicted label and your positive predicted label. Again, they correspond negative to 0 and positive to 1. And then you're going to look at each of those combinations, and they will have a certain name. So if we are here at the upper left corner, we call that one a true negative, and that's because the actual label was a negative label and the predicted label was a negative label, which means that we correctly classified this instance as negative, and therefore we call it a true negative. Similarly, you have the case where you have a positive actual label and a positive predicted label, and we call that a true positive because of course we classified it correctly as a positive. Then when we have a positive actual label but a negative prediction, then of course we make a mistake because it should have been a positive, but it is a negative, and therefore we call it a false negative because it was falsely classified as a negative label. Again, similarly, you can have the same argument for the false positive, where we assign the positive label, but it should have been a negative label. And these true negative, false negative, and true positive, you will see them throughout this bit of content. So first of all, if you see this, so we trained our model, we made predictions for each of the observations, and then we correctly put each classification in the correct bit of this confusion matrix. Then you could get something like this. In this case, we are going to classify something as spam or not spam in email. And we want to know a little bit more about how well our model did. So the easiest way to do this is just count the number of correctly classified instances. And that's actually done by just summing everything on the diagonal and then dividing by the total number of instances that you have. And this KPI is called the accuracy. So in this case, you see you sum 57 and 27 and divide by everything. Then you get here a accuracy of 84%, meaning we correctly classified 84% of the instances that we have. This sounds really nice. Unfortunately, there is a pitfall with this KPI. For example, if you have a imbalanced data set, meaning that you have, for example, way more positives in your training set than negatives, this metric can be misleading because, for example, in this case, you can see we classified 990 emails as non-spam, but only classified 10 emails as spam, but all of those were actually wrongly classified. So what you see here, if you calculate the accuracy, you basically get, you correctly classified 990 out of 1,000, which means 99%. But if you would just think a minute about this classifier, then you could wonder, do I actually want to install this spam classifier, for example, for my email? Because it actually never classifies anything as spam. Basically, you could also model this classifier as just something that always predicts non-spam. And then in that case, you just get an accuracy of 99%. So with this one, you need to be very careful on whether your model is actually doing what you want and not just looking at this number. Then here, it's more or less a question to you. For this session, it might be a little bit hard to ask someone to comment here, but I just want you to have a quick think about this one. So suppose you're the head of your IT department and you need to install a classifier, spam classifier for your coworkers. And then my question to you is, which of these classifiers, so the classifier A, which is on the left, or classifier B is on the right, which of these would you prefer? Just have a think. Maybe if someone can put something in the chat and maybe give a reason why you would like to use spam classifier A or B? I see Yuri says A. Could you elaborate maybe on that, Yuri, why you would use A? You can either do it in the chat or on mute. Yeah.
Yeah, I see. Yeah, let's say it was just a guess, not actually
Okay.
talking
No,
through
that's
it, to be
fine.
honest. But I see like a lot of predicted actual predicted, and I also see a lot of actual predicted non-spam and a lot of predicted spam. So in that case, it's really right. And yeah, let's say the 285 is spam, but it's not predicted. Yeah.
Yeah.
Yeah. So yeah, but that's it has a few false positives. That's how I see it.
Right. Thank you for that. I also see here someone that's saying something very similar. The first one because it gets more true spams. So I think that's a very good one. A because it also has fewer false positives. So the case of a false positive here means the positive here is a spam. And indeed, we have less things that are spam, but we did not pick up. And here someone's saying A has also a higher accuracy because it has 88 and B has 87. So thank you all for these comments. I think that's really nice that you comment on this. I think I want to just flip the perspective a little bit here. So I think I agree with all of you that if I would be the head of IT, I would definitely install the left one because I don't trust all my coworkers because I know you're just as strong as your weakest link. So I want to classify as much spam as possible correctly. And then I don't really care about, for example, something that was not spam but was classified as spam because that's for me, let's say, for safety. If you just mislabel a few things as spam, I think that's less of an issue than not labeling a few spam as not spam. But now flipping the perspective, if you would be the co-worker, I think you would be pretty annoyed that your head of IT installs something that labels your very important business mails as spam, because then you need to manually go to your spam folder and look for the ones that you want to read. And then actually you could miss very important information for your project. So I guess when you would be the coworker, you would likely have more something that if it makes spam classification, that it is really a precise classification, rather than having all your important business mails ending up in your spam folder. And this is also already showing you why, in certain cases, picking your KPIs for your classification project really depends on the context. Because really, in this example, it already shows you would make a different choice if you are the head of IT or you are the coworker. And let's also put this more in numbers. So indeed, as someone was already saying, the accuracy of model A is 88. The accuracy of model B is 87. But actually, we have also multiple things, multiple KPIs, which is, for example, the recall. So the recall captures the percentage of spam that was identified. So basically, out of all the spam that we have, how many did we classify correctly? So I think that would be 169 divided by the sum of these two. So you can see that classifier A has a almost twice the value of the recall of classifier B. But vice versa, the precision captures out of our predictions, how many predictions were correct. So you can see classifier A has only 71% classified correctly, and classifier B at 91%. So the 91, I think, here is, let's say you have 67 divided by 67 plus 7, which is then the 91 here. So basically, again, referring to either being the head of IT or the coworker. The head of IT might prefer having a higher recall, while the coworker might prefer a higher precision in this case. And there are actually more KPIs that we can look at, and also let's also put them into a formula. So the accuracy we already covered. So you're basically summing the diagonal by and then dividing by the total number of observations that you have. And you would use accuracy to answer the question, what percentage of emails is correctly classified? Then, of course, we have also something called an error rate, which is basically 1 minus the accuracy, and that captures, of course, what is the percentage of emails that is incorrectly classified. Then the precision. So you can look here at the precision, the true positives here, and you divide them by the sum of the true positives and the false positives. Basically, out of the positive population, yeah, and this is basically this column, the sum of this column. Mainly the positive population basically means all the emails that are spam in this case. Out of all those, how many did I classify correctly? So saying what percentage of predicted spam is actually spam. And the recall looks similar, but then we do the true positive divided by the false negative and the true positive summed. Again, this is basically everything that is spam, that is actually spam. And then we check out of everything that is spam, how many did we capture as spam? And therefore, the recall is used for what percentage of spam is correctly identified by the algorithm. Then we also have something called specificity. Yeah, I think I made a small mistake here. This one you can use for the question, what percentage of non-spam is correctly identified by the algorithm, by looking at the true negatives and then dividing by everything that is actually non-spam. Yeah, and very important here, because we always now talk about the positive and the negative label. Yeah, you decide which class is the positive and the negative. So basically all these metrics, they will flip if I would now classify or mark the spam as negative and the non-spam as positive. And that's also why this is sometimes confusing, because we always talk about positive and negative. But if something is classified as positive, if something is classified as a spam, is it then a positive or a negative? That is something you need to get used to. But I think nowadays we are a lot more used to these kind of labels when we have the COVID situation where we all did these these self-tests where you also get a negative or a positive label basically out of that test. And therefore negative actually meaning something positive for yourself. But just to note, this thing flips basically on how you assign the positive and the negative label. Then there are two more that I want to highlight here, and those are the false positive rate and the true positive rate. So false positive rate, again, you look at everything that you falsely identified as positive divided by everything that is negative. And everything that's negative is, of course, the first row here. So everything that's actually not spam, how many mistakes did you make? And then the true positive rate is the number of true positives divided by everything that is actually positive, showing you how many you correctly classified as spam in our case. And these are very important because we will see them later. These are commonly used to compare different classifiers. One more thing, because last time with logistic regression, we noticed that the output of the logistic regression is not a label, it is a prediction probability. So there's always this additional step that you need to deploy before you can actually label your predictions, and that is with this decision boundary. And you can actually see that your confusion matrix will change based on this decision boundary. Because, for example, if you would pick 0, which means that you only start to classify no, you start classifying something as spam if it has a higher prediction probability than 0%, which basically means that you classify everything as spam. Then, of course, the other way around, if you would set your boundary at 1, then your model needs to be more than 100% sure that something is a spam before it classifies it as spam. Therefore, it will never assign the positive label. And then if you put, of course, the 0.5 here, that's somewhere in between. But what you can actually see here, you can start sliding your boundary more to 1 or more to 0, and that will definitely affect all these metrics. So it's not just looking at the KPIs here, but also looking at the KPIs like precision, recall, and accuracy in the context of your boundary. And there's actually a method to do this, and that's called the recall operator curve, if I recall correctly, the ROC curve, and something called the area under the curve, the AUC. So this graph that you see here, each point corresponds to one specific decision boundary. So you can also see here that these ROC curves will always go to 0, 0, and 100%, 100%. And these points actually correspond to confusion matrices with a decision boundary of 0 and a boundary of 1. Because, for example, the true positive rate, if I can recall correctly, you look at, let me just look here. So true positive rate, we looked at the true positives divided by the positives. So again, the positives is the lower row, and the true positives, no, yeah, I'm saying that correctly, right? Yeah. So, or did we actually label them different? No, we did it like that. Yeah. So this is the true positive. These are the true positives. This is the positive row. So here you will see with the decision boundary of 0, you will get 100% true positive rate. In the other hand, you have 0 true positives, which means that the true positive rate is 0. And you can have the same, but flipped argument for the false positive rate. And therefore you can see that decision boundary 1 basically means we end up in 0, 0. And and that's basically because with the decision boundary of 0, you will never classify something as true positive, so as true, or sorry, I mean as positive, which means that you will have 0 true positives, and therefore it becomes 0. But on the other hand, all the negatives will be correctly classified, and therefore you didn't have any false positives. So therefore you also end up here. And similarly, you can have the same reasoning why you end up here with a decision boundary of 0 in the upper right corner of 100%, 100%. And then again, starting to slide, your decision boundary will result in all the other points on this line. The nice thing here with this ROC curve is that you can, let's maybe one too fast. Basically what you want in this classifier is that, or in this plot, is that you get as close as possible to this perfect classifier line. And this perfect classifier line basically says if I just change my decision boundary to, let's say, 99.99%, and then it starts classifying everything as a spam, meaning that the model is very, very sure on its predictions. And that's why the perfect classifier basically jumps to 100% directly and then stays at that 100% here. And then whenever you start lowering your decision boundary, of course, you will start to make, no, you will actually, sorry, I mislabeled that. The idea is at least that your true positive rate skyrockets to 100%. And there's also this additional line here. It's basically this 45-degree line. And that's basically just the coin flip. So the coin flip here is this dotted line saying that, yeah, I will probably make a 50%, and with a 50% probability, a correct classification. So whenever you're close to that line, that's basically not good. And the nice thing, what I was already saying a little bit here, is that this graph can be used to compare models, because the closer this ROC line gets towards the perfect classifier, the better your classifier is performing. So you can do this with the graphical representation, just showing all the ROC curves in one plot. But what you could also do is calculate the area under the curve, and that gives you one value to compare each classifier. Basically, the area under the curve is really just how much of the total, this 1x1 block is covered by my ROC curve, meaning that if I get something that is 1, then I have my perfect classifier, because I basically have the area under the curve is 1 times 1. And basically the worst model goes to 50%, because it's exactly half of the total block. One thing you might have noticed here is that all the graphs are above this 50% line, or all above this, random classifier, or I call it classifier with no predictive value line. And that's of course because whenever your line would be below the random classifier line, you can actually just swap your negative and positive label, and then basically the line gets mirrored across this 45-degree line, and then it ends up again above this line. So you will always see a RC curve with only lines above this 45-degree line. And really the nice thing about this area under the curve is that you can just calculate it for all your models and then just have one value to compare them. Of course, you should not just look at that one, but it's a nice way to have a more generic comparison between the classifiers. So far, we learned that for regression, we can use all these mean absolute error, mean absolute percentage error, so mean squared percentage error, for example. For classification, we start using the confusion matrix and using those KPIs like accuracy, recall, precision. But we have to note that accuracy alone is not just good enough, because it can give a misleading result. And therefore, we also need to have a look at other measures like precision or recall. Here, very important is that the ordering of the confusion matrix matters. And of course, that's again the bit about the labels. If you swap the labels, then the precision and recall KPIs will also swap. So that's important to note here. So this is all about what kind of metrics or KPIs you can calculate to assess the quality of your fit. But now we have not covered how do we actually know our model will perform okay when we would, for example, put it live and start making actual predictions in real time, for example. So we also need to learn more about can we tell something about the forecast actually? So really seeing when it sees something new it has never seen before, how well is our model going to do? And that is in the end the one that's the most important, because that gives you some idea of the performance in real life. So the simplest approach that you can do here is split your historical data into training and test data using a train test split. And then of course you train the model on your training data, and then you use the test data to estimate the quality of the model. Important is that your model never sees test data, because then it's not a fair assessment. And again, yes, the idea here is that with this validation set, we can now start to see if we are in the high bias or the high variance case. Because what you can do, you can calculate, for example, the R² on your training set if you're doing linear regression, and you can calculate your R² on the test set, and you can compare those two. So if you see that both of them are very low because they are close to zero, then you're probably in the case with a high bias. But if you have, for example, training R² of 1, meaning you have almost no training error, but your validation in R² is, for example, at 0.5, meaning you have quite some errors, then you can see that actually the performance on the training and the test is very different. And then we're actually in the case of high variance, because probably you're overfitting on certain bits of information in your validation set. In your training set. But when both the validation and the training are very similar, so they're pretty close, and they're reasonable, they have a reasonable performance, then you might get a feeling, okay, now we start to be in the zone between the high bias and the high variance, and that's of course where you want to be. Right, yeah, we don't need to recap here, but the difficulty here is the way we're going to do the splitting, and because in the end you might have just a limited supply of data, and now you need to set stuff aside. So maybe there are better ways to do it. So there are basically 3 different ways to test your model, and one we have already discussed, which is the validation set approach. So again, validation set approach, you just do one random split, maybe into halves or maybe something else. And one is labeled as training and one is labeled as validation. And then you start to do testing and training. And what you might already see here is that the way you split has impact. Because if you have 100 data points, you can end up with quite some different I say that combinations of training and test sets. Meaning that, for example, if there are like very important observations that you really need your model to learn on, but you put them in your test set, then the model cannot pick up on that bit of structure or on that bit that they actually need to learn on. So the performance of your model is very likely to be dependent on the split that you make. So here you can see, I'm not so sure what the one on the left is, but on the right here you can see if each of these lines is basically a different way of splitting your historical data into training and testing, and then each of these are, so again, on the x-axis you see the complexity of the model, and on the y-axis you see the error. So you can see just basically the way we split our data has a massive impact on what kind of performance we get out of it. That's of course not really desired, because then maybe you ended up accidentally with the best training test split, but that might not be a really representative train test split or representative performance, because this might be too optimistic, for example. Just something that from practice here that I can give an example on. No, that's a little bit too early. I will give the example later on. So there are definitely drawbacks here. One drawback here is that you need to set aside a real large chunk of your historical data, and that actually could lead to overestimating the real error rate. That might sound a little bit too not very intuitive, but the idea is that if you just end up with, for example, 50% of the data that you have for training, then of course a model that would have been trained on 80% of that data might have done better. So you might get not really a realistic performance of the model. And of course, what I already mentioned, the way you make the split has impact on the error rate of your model. But there's one, we will see later on why this has a, I can also mention it right now, but there's of course also a real plus side on this is that it's really easy to deploy, to execute, because you can just, I think we saw it yesterday, there's just this Python function called train test split, I think, and then you just pass your data there and then you're basically done. So typically, whenever I do a new project and I just want to get some results quickly, to just get a feeling on the data and what kind of performance I could expect, I just do a test split first, and then I at least get something going already. But there are actually probably better approaches to get a better approximation of the performance of your model. One of those is the leave out one cross-validation. So what you're going to do, suppose you have, let's say 100 data points. What you're going to do is you're going to make 100 splits. And in each split, you're going to leave out one data point and then train on the rest. So here at the first row, you see we're just going to leave out data point number 1. And that will be our, let's say, validation set. And our training set will be the rest. And then whenever I calculated all my metrics on this one, I do a new so-called replication of my experiment. But now what I do, I leave out observation number 2 and train on the rest. Again, I calculate the performance and I move on to the next replication. That replication, I'm going to leave out 3, and so on and so on. And basically, you're going, in the case of n equals 100, you end up with 100 replications where you, at each stage, at each replication, just leave out one data point and do the training and testing. So what is important here is that because we do 100 replications, you need to train and test your model 100 times. And then, of course, you also end up with 100 KPIs. So, for example, if you would use the mean squared error, then you would get a mean squared error for the first replication, the second, and up to the end. So what you would do is you would take the sum of all those mean squared errors and then take the average to get the actual test error that you are interested in. And we also have a slightly different version of this, and that one is called k-fold cross-validation. So instead of always leaving out one and training on the rest, we're going to leave out k no, sorry, that's not true. What you're going to do is you specify how many replications you're going to make. So if I set k equals to 5, which is this example, I'm going to split my data set into 5 chunks. And then at each replication, I use 4 chunks for training and 1 for testing. And then in the next replication, I'm going to pick a different chunk to set aside for testing. And then again, I'm going to train on the rest. So again, based on the K that you pick, it basically specifies how many replications you're going to have. Very similar to the leave out one cross validation, you are going to take an average of all the KPIs that you calculated during at each replication step, and then in this case take the average of the mean squared error again. And this is in the end the one that you're interested in. Typically, what is also interesting, it's not just the average, but what you could also look at is the standard deviation and the variance, for example. It also gives you an idea on the spread or the variance between the different splits in your KPI. So when, of course, in the most optimal case, the leave out cross validation is really you get a very good assessment of your quality. But what if you would look at the performance of the different replications at tenfold cross validation, you can actually see that the mean squared errors, they follow the same trend. So what you can actually see already with the tenfold cross validation, we get very similar observation with the error or the mean squared error. I see a question.
Do you hear me, David?
Yeah, I can hear you.
I just do not understand this graph. So could you explain me?
Yeah, I will explain it one more time. So here, this graph basically, so if in the case of, let's say the linear regression model,
Yeah.
you can basically see the degree of the polynomial. In this case would be the number of features you would use.
Mm.
So in this case, the more features you add to your model, the more complex it gets. And what you typically anticipate is that whenever you have a more complex model, your error decreases.
Mm-hmm.
That's typically what you would assume. So I don't know how exactly these points were drawn, but it's just for the example purpose. And then here on the y-axis, you see some kind of KPI. In this case, it's the mean squared error. So for example, for a linear regression model of degree 1, so just one feature, we would have 24 point something mean squared error. And then whenever we start making it more complex, you would get a different mean squared error. And the thing that you, so that's the first thing that you need to see here. And with leave out cross validation, with leave out one cross validation, this is basically the average of each of these points, each of these replications. Important here, and that might be not so intuitive here, is that this point here is basically the average of 100 replications. And this one is also an average of 100 replications, because if you want to make such a graph, you're basically going to do this leave out one cross validation for a linear regression model with one feature, and that results in this value. But then also you're going to do it for a linear regression with two features, that results in this uh, data point, and so on and so on. And that's basically also what you see here, except that the only difference between what we have here on the right and the left is that one of these lines corresponds to one way of splitting your data into 10 chunks and then doing all these replication steps. Of course, when we make these chunks, there are different ways to construct the chunks. So what you see here is that one of these lines corresponds to one way of organizing or making these splits. And another line is a different way of splitting. And then we plot them all in one graph just to see, do they show comparable, how do you say that? Yeah, behavior. Yeah. Do they look similar, or do we see really large variance between those different experiments that we did? And what we can conclude from this is that already with tenfold cross validation, we get something that's pretty stable. And later on, we will see, in the next slide, I will show you why in certain cases you want to use one or the other. I see there are a little bit more questions. So does the size of the data matter? Yes, in a lot of ways. So maybe that's that one I can actually do in the next slide. So let's just compare the three different methods. So as we already mentioned, the validation set approach is pretty simple because you just do one split and you're done. But it's highly variable. The issue with the upside with the leave out cross validation is basically there's no variation, right? You cannot split your data any different because you just leave out one, so there's always the same result. And therefore, you also get a better approximation of the actual performance of your model. One issue with this leave out cross validation is that it has very high computation time. And this is also where the size of your data really matters. So suppose you would have 3 million data points. What you're going to do with leave out cross validation is you're going to leave out one data point and then train on the other 2,999,990. Yeah, I think you get the picture. So you're going to make a lot of replications. So suppose it would take 1 minute, and I think that's already a little bit large. So suppose it takes 1 second to train your model, then it's already going to take 3 million seconds to calculate the model performance using leave out one cross validation. So although this might be theoretically the preferred way to go, practically I think you will never use this. And that's why typically you only use the k-fold. Yeah, you should always use the k-fold cross-validation. Of course, it's a little bit more complex than the validation set approach, but the upside is that the computation time is a lot smaller. So again, based on how much data you have, you either pick case 5 or case 10. Of course, case 5 you can also pick that if you have a very complex model, for example. But yeah, I would typically just recommend, it doesn't really matter. If you can go for 10, then you should go for 10. I think that is typically a better one to use. But yeah, it's just, again, you can play around, and it depends how much data you have and how complex it is to train your model. Because, for example, if your model takes 10 minutes or more to train, for example, you could think about neural networks or something, then it doesn't make any sense to do 10 replication, because then it's just going to take a very long time to actually do this. The upside also here is that it has less variance, so it has a small bias compared to the one that we want actually with the leave-out one cross-validation. So here there's actually no downside. So the only downside that I can think of is that it's pretty, at first you might be guessing what kind of value for K you need to do. So there's one more additional complexity with picking a new parameter when doing training. So I think that is maybe the one downside that you have here. Hope that answered the question here with the size of the data. So yeah, that's basically everything I wanted to discuss about model quality and and how you should validate the performance of your model. I think now it would be a nice time to get started on the project. So let me just introduce that. Let's see. So in the again on the GitHub, you can find course in the coursework. Now I'm actually lost in this. Yeah. So here in the machine learning 101 and hands-on machine learning, there's also this day 2 folder. And here there's just one exercise folder called the classifier project. And in this one, you're going to have to deal with a data set related to water. So with this data set, you get certain measurements about the water. So what's the pH value, for example, of the water, and you need to estimate whether it is potable, yes or no. And the one thing that you can see here, what I already did for you, is import some important libraries and functions that you should use. So if you want to get some inspiration, you can just look already at the libraries and the functions that I imported for you, and then you can start trying playing around with those functions. So what I already did for you, I filled in some cells to load the data, properly transform the data to the correct data types, because that is important typically when we're doing classification. And in this data set, there are apparently some missing. So what I do here is I fill in some mean, so yeah, some kind of a good guess value for all those missing values. So you don't need to deal with that yourself. And what I already did for you is create the X and the Y data sets, and then up to you. Already give you one hint that you can use a train test split first and just play around. But then actually it's up to you what you want to do. Again, if you feel lost, what I did is I created in this README file on the GitHub some kind of a step plan that you can follow. So basically, maybe just start with the train test bed first, train the model, and test the model on a validation set, and then improve one step basically by doing, instead of a train test split, use a cross-validation approach to check your model and play around with the decision boundary to see what kind of performance changes you see of your model. What I typically have, I've never seen people get the time for is actually do ROC curves. So I would probably just recommend doing this step plan multiple times, but then with different techniques. So for now, what you can do is get started with the logistic regression, because that one is used for classification. You can already try to do this cross-validation approach for that technique. And then I think in an hour or something, depends a little bit on how fast you are going with the exercises, is we will start introducing new models. The next one will be decision trees. Then again, you have the time to play around with the decision tree. And then afterwards, we will again have one more set of theory where I introduce, for example, random forest. And again, you can go back to your project and play around with random forest in there. And then in the end, you should end up with a notebook file where you have trained different models with different techniques, and something that tries to compare them. That can either be just with the metrics that you picked, or if you're really fast, also with ROC curves. But I think that's probably out of, you won't have enough time to actually create an ROC curve. One bonus, but that's actually just for when we are starting work on the decision tree bit, is that there is a nice method that you can make a graphical representation of your trained model. So I would definitely, when you start training a decision tree, use this plot tree method to see what you actually created. I know that it might be difficult, at least that was what I experienced last year during this day, is that I would prefer to go into breakout rooms. And then if you want, you can actually work together on the project. But I know last time that was not really a success. So let's see if you want to work together. So please, in your breakout room, discuss how you want to approach it. What I will be doing is hopping from breakout room to breakout room and answering questions. And with this project, I think it's not doable to have a, let's say, one planar session where that would be just too chaotic, I think, and because everyone can do whatever they want to do with this project. Again, please go to the Google Colab, and then upload your data like yesterday there. I think what we're going to do is I will give you 1 hour. That's maybe a little bit too long. I think decision trees is more interesting to work on. I will give you 45 minutes, and that also includes already your break, because I can imagine after this 1 hour, you might be, that's a little bit too much information in one go. So just take a break whenever you want. So the 45 minutes also includes a break, and then at 45, we will, proceed with the next bit of theory. At the end of today, we will discuss the results together. And so I will reserve some time to show you how I did the project myself. I see someone asks for the link. I can definitely do that. And if you're really stuck and you don't have any inspiration, I already uploaded the answer notebook, but that really also contains custom codes that I created myself at some point. So this one might be more difficult to read yourself, but at least it can give you again some inspiration if you're stuck. All right, and let's see if it's going to work with the breakout rooms. So we are with 35 people, which means I'm going to make, I think let's make 9, no, let's make 8 breakout rooms. So it's 4 to 5 people in one breakout room. That's doable, I think. Oh, it's already saying it here. Cool. So you will be assigned to a breakout room automatically. and then at some point I will hop to your breakout room for questions. I think what you can also do is chat to me or in the general meeting chat if you really have some burning questions, and then I can prioritize hopping to your breakout room first. So good luck with the project, and I will see you here back in 45 minutes. So hi everyone, welcome back again to the general session. We will start uh, with some new bit of theory, but before that, I won't do any walkthrough of exercises right now. Just had a quick look at the answers that I had. I think it would be most beneficial for you all if we take a little bit more time after you worked on the decision trees for a bit, that I can show you what I did for decision trees, that you can use it as inspiration for the last coding session after that. But besides that, what I noticed, and that's pretty similar to what I noticed last year, is that most of the breakout rooms are pretty quiet, which I assume that's fine. By the way, I mean I know that not everyone is able to work together like that, or it's just not possible, or you want to work on your own. That's all fine. But I also know that there are always people that would like to collaborate a little bit, because it's valuable to learn from what everyone already knows how to do. So if you want to be in a breakout room that has a little bit more, how do you say that, communication and more interaction, then please let me know that in the chat, because then I can group the people together that are able right now to collaborate, and that is possible for them, such that at least you guys you can enjoy the collaboration of the breakout room. Before the first session, there was a good question that you are not able to share screens. I think we have fixed that right now, that you can actually in a breakout room share the screen. So that should be possible. Um, so yeah, in the meantime, please put a message directly to me maybe, or just in the main chat. I mean, that doesn't really matter. And then I will try to group the groups slightly different for the second session. All right, let's move on to the next bit of theory, which will be the decision trees. So the decision trees can actually be used for multiple ways, or multiple machine learning projects. You can actually use them both for regression as well as classification. I have to say that the regression one is slightly more complex, and we will not really cover in this course. At least at the end of the course, I will, at this bit of content, I will show you how you can do it. The main content will be about the classification. Um, then let's move on. So why is it actually called a decision tree? It's actually because it really looks like a tree. Because the idea is that at the start of your tree, yeah, it's basically, you could say, an inverted tree. So at the start, the root of the tree, you basically have all your data, and the idea is that based on a certain split, you're going to bit to a new branch. So here, example, we have we want to predict whether someone has more or less risk on getting lung cancer. And in this case, the first question that we ask when an instance appears here, is this person a smoker? Yes or no? If so, yes, then we pass this instance to the yes branch. And if no, we pass it to the other branch. Then in those new branches that we have, we can make splits again. Notice that you can actually have different splits in the feature in the other branches. So here in the left branch, we do our next split on age, while in the right branch, we do our split on diet. And then based again on some kind of a split. So in the first case, it was like a binary split, so yes or no. But in age, you get, of course, more. You can put a numerical value. So if you're below 30, then you have less risk. But if you're older than 30, you have more risk. And diet is again something more like a categorical variable. You say either when good, then less risk, and again poor, more risk. So this is basically how a decision tree works. These decision points, so to say, we actually call them nodes. So the smoky here is a node and age is a node. And at each node, we need to make a split based on the attribute in your data set. The nodes at the end of the branch are actually called leaves. So at leaves, we don't make any additional splits. So let's show you how you can actually use a decision tree. New York. So it might be a little bit difficult to see from this overview, but the first feature that might appear like a good one to split on first is the elevation. So if you would make this plot, then you can see each bar basically represents a house. Whenever the bar is a little bit denser or darker, that means there are multiple data points overlapping. Basically, you see each house in San Francisco and New York and their elevation. So what you notice is that there are no New York houses above 240 feet. So maybe that might be one of the splits that you could first do. So you could say whenever a house is above 240 feet, go to the right, and if it's below 240 feet, go to the left. And then we could say if you're on the right, we know it's San Francisco, and maybe in the left. For now, we say it's a New York City house, but maybe we want to refine that in the end. So the first split would be on 240 feet. But of course, we have more data available. So instead of just looking at this one-dimensionally, we can also look at this in 2D. And in this case, we have the elevation on the y-axis, and we have the price per square feet on the x-axis. So what you see when you add this new dimension is that when normally everything would be basically on one line, all these data points, what you do now is basically you drag it across this new dimension that you added. So you can definitely see that having multiple attributes in this case has some meaning and gives you some more information about each data point. So what you can see here is that around $1,776 per square feet, there are basically no houses in everything more expensive than that is basically only New York houses. So that would also be a nice one that we say, okay, we know 240 feet and 1776. Those two give me already a good first guess. So what you can see here, if I use these split points, then basically what you're going to do is that every time a data point falls in this rectangle that is denoted by 0 to 240 feet and 1776 to $4,600 per square feet, then we're going to classify this as a New York house. And we could also have the same, but then everything basically above 240 feet, this whole block, you could also say whenever a data point falls in that region, now maybe that doesn't make a lot of sense, but maybe more like 200 feet up and everything below the 1776, that should be a San Francisco house. Then of course, the thing that we still need to do is everything that's in this block that's squeezed between these two blocks. So where you can basically see that there's still a lot of clutter. So there's no clear picture, at least based on these two features, to separate or right now these data points. But first of all, what we have currently just done is just picked, of course, a random, not really random. We looked at the data and we picked one split point. So for our initial split, it was 240 feet. And at least we can already check based on this split, how well am I actually already doing? So if I would just use this split and then use majority voting in the leaf node. So again, it was maybe a little bit too fast. So basically, at the first node, we have our data, and what we're going to do, we're going to split on square feet. Elevation. Everything below 240 feet will go to the left branch, but we are not making any additional splits. So you end up in the leaf of the decision tree immediately. And then on the right hand side, we also end up now we end up with everything above 240 feet. So what you see, if you would use majority voting, is that when you end up in the right leaf node, you will classify it as San Francisco, and here we make 0 mistakes. On the other hand, if you would end up in the left branch, you can actually see that based on the data that we have, and majority voting is that we're going to classify everything here as a New York house, which means that we're going to make 92 mistakes because actually 92 of them were San Francisco houses. So overall, we are now currently having a correctness of 63%. Again, San Francisco houses here are, you could say they are called the false negatives whenever you would label New York as a negative and San Francisco as positive. So my question here is this actually the best we can do? Because here we're actually making mistakes. Can we pick a split such that we don't make any mistakes? Well, yes, we can do that, but in this case, it doesn't really help us. So what we could also do is to say, let's be very safe, and we're going to say just put it at 0.0, such that we capture each San Francisco house in the right leaf node. But when putting it at 0 elevation, basically you end up with all your data in the right branch, which means that you're going to make apparently 111 mistakes, and in the left leaf node you end up with 0 data points. Then of course this split is not really helping you because it doesn't give you any information, but at least shows you that given my split, I will get different correctness in my first split. So of course, now the question is, can we actually do a best split? And of course, there is some mathematical method to do that. And if we would do a best split on elevation, you actually end up with a split point at 91.9 feet, which might surprise you because then right now in the first one that we used, 240 feet, we were actually in one of the leaves. We didn't make any mistakes. But now actually what we say, because we know we can make multiple splits, we don't need to end up with, let's say, something called a pure node. And pure meaning just having one set of labels there, so only San Francisco houses, for example. The target is more that we want to make both of these leaves as pure as possible. So of course, what we had before is that in this case, making this leaf node pure resulted in a not so pure left leaf node, because here it's basically 50-50. So what you can see here, here it's like 90% or something is San Francisco, and in the other one it's like a quarter, so 25%, I mean. So apparently using this, you can actually see we boosted our correctness if we pick this split. Then the next thing is, of course, the algorithm, so if you're going to do this in Python, the algorithm will split first on elevation, calculates the best split for you. What you can actually then do is just make a new split in each of the branches that you have. So here in the left branch, we're going to do a split on price per square feet. On the right branch, we're going to do a split on price. And basically, yeah, they call it a fork, this, and with this, you're actually going to increase the prediction accuracy of your tree, because you're going to refine your split, and again, making these leaf nodes as purer, basically. Of course, it doesn't stop at just 2 splits that you can make. You can actually do more. So here we just ended up in the right, at least you can see we ended up with a lot of pure nodes. So this one is pure, pure, pure. So at least we have 1, 2, 3, 4, 5, 6, 7 pure nodes, and just one that is not pure yet. Note also that the size of the leaf node basically means how many data points end up here. So you can see we might not really care about just 2 data points ending up here, because then okay, we will probably never be 100% accurate. So basically you can just grow. However, in most cases, it's actually possible that I think in most cases, I'm not sure, it might be all cases, you're actually able to grow a tree that will be 100% accurate, meaning you just grow your tree until all your leaf nodes are 100% pure. And then here you see in this example, basically all the leaf nodes are just contain one set of labels. And that actually means that when you would predict on your training data, so basically the data that you train on, your predictions will be 100% accurate, because each data point will end up at the correct leaf node here. But now, of course, you might have seen it coming.
Excuse me.
Yes.
Allow me to ask. How does the model order the features? And is there iteration in it, or once, for example, say sulfate is the first feature that has been used to do the splits, or the elevation that has been used to do the splits, can it be used again, or that's it?
No, yes, you can actually already see it. So here elevation is used at the top, and the letters are really small, but you can see elevation is used here, and then elevation is also used here, elevation is also used here, and elevation is also used here and here. So yeah, definitely it's possible to have a multi-split on one feature. So just using it once doesn't exclude it from being used later on.
Okay, so and does that mean then it's not there's no need to think the model doesn't order the way in which the features are being used to do the splits? Is it sort of like it's random? It can start with age and then go to
There are
sex.
multiple ways to do that. So it depends a little bit on how many features you have. So what it could do is, I have to say for decision trees, I don't know for sure. I'm not sure whether it considers all features at each split, but basically it could calculate. So basically what it could do, it picks one feature, it can pick multiple split points for that feature, calculates how well or how pure my nodes become when I use that split. And then I could also calculate it for my other features. And basically I can pick the one that gives me the purest nodes. And that's basically how the algorithm chooses whether to split on price per square feet or something else. So there is some kind of a algorithm that picks the feature. So when you do it in Python, you don't need to care about the splits, because that's done by the algorithm. Okay, cool. Also, I will also show you a little bit more how you can calculate what the best split is. But for now, when you look at this, basically this decision tree that got 100% accurate, you might wonder, but we learned about this overfitting, underfitting. This really looks like overfitting, because if someone mislabeled, for example, data points, then that data point will end up in its own leaf node, for example, meaning that every time a similar data point comes in, it will also be misclassified just because someone made an error. So what you typically see in this case, if you calculate the training accuracy and the test accuracy, that those are not the same. Meaning training accuracy is 100%, but your test accuracy is not 100%. And when these two don't match, and there's a big difference, then you're probably overfitting. So this is a good indication in our case that we should improve. And the question is, how should we improve? And that's actually pretty straightforward. So what we could do is we can just restrict the tree to not grow indefinitely, basically. So and indefinitely, I mean keep growing until I have pure leaf nodes. So what I can say, for example, never grow more than 2 splits. So you can see after 2 splits, I'm not allowed to split anymore, and then it stops. In this way, you might have a lower training accuracy, but your model becomes more robust. And this process is actually called pruning of your tree. Yeah, so we don't need to do that. Right now, the question is, of course, how do I won't go into the mathematical details, but I just want to give you a feeling how it chooses it. So first of all, the question here is, what should be the target when we do a split? So although I have said, of course, that leaf nodes should never be pure, but what you of course try to do is with each split that you make is make each of the leaf nodes as pure as possible. So what you always target is trying to have all the leaves or all the nodes that come out of your split to be as pure as possible. So actually you want to target C as much as possible, although that might not be always possible. So what you do, because you always, when you do a split, you don't get just one new node, you get always multiple. So what you do if you have, for example, 2 classes, what you do is you're going to calculate something like, for example, the entropy or the Gini index or the error rate. That gives you some measure on how pure a node is. And basically, whenever these metrics either say 0 or 1, then you have the purest node. And that's because, for example, if we would look at Gini index, because I think that's probably the most intuitive one to look at, P underscore I basically means the proportion of class I, yeah, at that node. So if you have 2 classes, it's basically you have P and 1 minus P. So whenever you have a pure node that only contains 1 class, PI will be, or the P will be 100%, and this one becomes 1 minus 1, becomes 0, and that's why you end up in with a purity measure of 0. So that also holds in the case that the P is, for example, 0. Then of course, because we have 2 classes, it means the other class is 100%. Sorry, the other way around, I think. So if this one is 1, then the other one will be 0, and again you end up in 0. And the worst that you can do is that if you have 2 classes, that they are 50-50. 50-50 in this case means like 50% times 1 minus 50%. Again, you end up in I don't know, that should not hold, right? Oh, sorry. Yeah, you're going to do it for 2 classes. That's a little bit the issue that I have here. So if you have 2 classes, you sum twice 0.5 times 0.5 plus 0.5 times 0.5, but you end up at exactly this 0.5 that you see here. So in the case, if you choose your Gini index, the purest node has a purity measure of 0, and the one that has a 50-50 split ends up with a purity measure value of 50%. This is something you can choose when you train a decision tree which one you want to use. So this is typically what you see when you have a decision tree. There's something that you can specify that you want to use Gini, for example. Typically, I think Gini is the default because it's the easiest or the not as expensive to calculate as the entropy, because here you can see you need to calculate some kind of a logarithm. So computationally wise, this one is more efficient, but it also gets the job done. And basically, what you want to maximize when you do a split is the information gain. And that's basically the information gain is the difference in the or the purity of the node before the split and, for example, the average purity of the nodes after the split. And the difference between that is the information gain. And basically, when you're going to do a split, you want to maximize the information gain always. But that's it. I won't dive any deeper in the calculations. One additional note that I want to make on overfitting for decision trees, we have multiple options. So we can actually specify, for example, the maximum depth of a tree. I think the depth, it's always a little bit confusing to me, but I think the depth is how many consecutive splits can I make. So if you would say 9, I think what you can do is you can make the first split and then do another split and then another split and then basically 9 consecutive splits, and then the tree should stop. Then what you could also do is you say maximum number of leaves. That is pretty different because it just shows you the depth of the tree. But if you just specify the maximum leaves, you can have a very different shape of your tree. And another one that's nice to use is basically saying minimum number of observations in leaf nodes. So basically you could say a leaf node should never contain less than 10 observations. Of course, this really depends on how many data points you have in your training data set. But in this way, you can make sure that the tree doesn't grow until it has just one data point in one leaf, because I think that's typically the default. And the minimum info gain, that one is I would not really recommend to use, but you can also say when I make a split, at least I should get this additional information out of it.
Why would you not recommend to use the minimum info gain? Because to me it
because
seems
for me, the issue with the info gain is you need to specify some kind of a number, and to me the number doesn't mean anything. So suppose you would set the info gain at 0.05, then for me that's not so intuitive to interpret. I think, but definitely, I mean, you could do it, but then especially for this exercise that you're going to do, I think it's more intuitive to use the other ones. But of course, in your own project, use whatever one works best for you. I won't cover how you would normally do that, but if you're interested in that, there's something called a grid search. And grid search, basically, you can specify a set of options that it should check. So for example, for the maximum depth of the tree, you can say I am interested in 5, 10, 15, or indefinite. And then the grid search will just check all the combinations that you specify. And in that way, you can actually have a better understanding which one works best for you, instead of just looking at the ones that are intuitive for you. But especially for now, just stick with the intuitive ones. The only downside, the last thing I will mention about this with grid search is that the issue here is really that, it's the curse of this dimensionality. Because if you pick 5 options for the depth of the tree, 5 options for the number of leaves, 5 options for other ones, then it's basically going to check 5 times 5 times 5 different decision trees. And then if you want to do cross-validation, then it's 5 times 5 times 5 times 10, for example. So you're going to train a lot of models. So I don't think for decision trees it's an issue. But if you have computationally intensive things, then grid search can take years and years, for example, to compute if you pick bad inputs there.
Okay, thanks.
Again, what you could do instead of the grid search that I was talking about, what you can do is something very similar, like almost like an elbow plot, is just vary one of the features and then see how your validation error and your test error change based on the number of leaves, for example, or some other kind of it's called, by the way, a hyperparameter that you want to choose. So hyperparameters are the parameters on models, just like the number of leaves or the depth of the tree. But this is really more advanced. So for now, and that's why I also recommend it when you're going to train decision trees, please make sure that you do a plot tree. So basically making a graphical representation of the tree that you make, because then you can actually see what it means when you use a maximum depth of 9 or a maximum depth of 1, because then you really see that the shape of your tree changes. I think for now that's more important than really trying to optimize the parameters, but just know that there are ways to do that. And typically, not typically, you should always use cross-validation to check different, for example, choices of the hyperparameters. Yeah, so for now, I don't want to specify and say anything about model trees because those are really complicated and really out of scope. But right now, what I've only been talking about is classification trees, so that you can use the decision tree for classification. But what you can also do is just do regression with it. And for classification trees, you basically do majority voting at each leaf. Basically meaning that the one with the highest proportion will be the label that you predict. When you have regression trees, what you will do, all the data points that end up in that leaf, you will take the average, and that will be your prediction of the target. But just for you to know that you can do regression with the decision tree, but I have to say they're not really accurate. And that's basically that always holds for decision trees. You will see that they are in general, they are very intuitive. They are really interpretable because when you train the model in Python, you can actually just request at each node what kind of split it did. So you can always explain how you came up with this this prediction. But yeah, because of the interpretability, it's not as accurate. But in the last bit of theory, we will see how you can actually boost accuracy with these kind of models. So that's it. What I want to talk about about the decision trees. Let's see if there are any questions. I think there's more. I will go through the longer post after this. I don't see any questions. So again, I will open up the breakout rooms, and I will try to remap the groups such that some people can work together, and I will have a look at the longer post that was put in the chat. Let's see. All right, welcome back to the main session. First of all, yeah, I was a little bit. Yeah, I feel very sorry to hear that for certain people this is going a little bit too fast. So especially thank you for raising the concern. Unfortunately, there's not a lot of time to play in on that. So what I'm going to do now is have a little bit more of a session to also show you why we have this project already today and why everything is not as complicated as it looks maybe when you're doing this hands-on stuff. So I'm going to do a little bit of a live coding session right now, and then I'm also going to show you how I actually approach the decision tree bit and the logistic regression bit. And then I will make sure at least we have enough time to do the theory of random forest. I don't know whether we will have enough time to actually also do some hands-on bit, but again, that is just a very minor adjustment to what you have been doing so far. At least I want to make sure that I also show you how I approach the random forest bit. So first of all, I think, no, I'm not. Let me share the screen. So basically these lines of code, I think I've already discussed. So here I read the data. I always check a little bit what kind of data do we have to just understand what we are doing. Here I'm just making sure all the columns are read as the correct data type. And here you can see there are like quite some missing values. So that's why I needed to fill in those missing values with some kind of I think here I use a mean, but that doesn't really matter for now. Important here is that there shouldn't be any missings because machine learning models cannot deal with missing values. Here I split my data in a feature set. So I drop the potability column and I only keep the feature potability because that's my target variable. And then here, what we are going to do, because probably for now, because it is maybe your first project, you want to start with just a simple train test split. So this is basically the line of code that you could have copied from yesterday's exercises. I think we did it in the logistic one. I don't know whether it was logistic or the linear regression one, but this is basically the same line of code. Here I specify stratify. What it means is basically you want to try to have, let's say, that the true and the negative, the positive and the negative causes are well presented in both the test and the train set. I think that is what this stratify argument is doing for you. And then I make sure my test set is 25% of my data. And you can actually see that when you look at the shape of your data, that it also holds. And that the train ones have the same number of rows and that the tests also have the same number of rows. And now what I first want to show you is the lines of code. Let me just remove these lines of code and let's do it together. And let me show you how I typically do this kind of stuff. So first of all, I want to train the logistic regression one because that's the one that we learned yesterday. So logistic regression, you don't need to specify anything. You can just make an empty instance here. And then I'm going to train the model. And basically these lines of code make sure your model is trained. That is actually what we have seen yesterday. And you can actually test that this thing is trained by doing, for example, a predict. Because if I would have a logistic regression and a logistic regression that is not trained, and I would now do a predict, then it should raise an error that you can see your instance is not fitted yet. Then I want to do some basic testing, for example. So what I can do is I do Y prediction of my training set using my linear regression model. So that's basically how I name my variable. So the Y predicted of the train set of my linear regression model, logistic regression model, sorry about that, is doing the predict of the train set. And I can do something similar for the test set. Again, these are the lines of code that we also used yesterday. And of course, we are interested in the scores. So what we can do is, for example, look at the accuracy score because that's the most easy one to look at for now. So what we need to do is we need to put in the actual values of y, which are in this case y train. And then I'm going to put in the predicted ones, which are predict train linear regression, logistic regression, and I get a value of 0.6. Similarly, I can just copy this line of code and swap this one with y pred the test, and also, of course, I need to change this one to test. And now I already get 2 values, so you see these are pretty similar, which is of course something that we want, but they're not particularly good or anything. Then, of course, what you also want to do, maybe if you want to dive deeper, is make a confusion matrix. And I think that's basically, again, you do the same thing. You ingest your y true, which is again, now in this case, I'm maybe only interested in the, I can actually make them, I'm only interested in the ones for validation set. So here I put in my y prediction, no, my test. And I'm going to put in the y prediction as y prediction test. And I get my confusion matrix. So here you can already see, although I got 60%, this model doesn't seem to do anything. And we can actually also do that test. For example, if I check the precision score of my, no, just going to copy this. You actually see that the precision is 0, which is not really really good. But now, actually, what you could do is say, instead of a logistic regression thing, what I want to do is train a decision tree. So although my variables all only contain already kind of reference to my decision tree, I just want to show you how easy it is to swap between between methods. So I can now just run these lines of code again, just swapping the classifier, and now I get different values. So now you can see my accuracy score of my decision tree is 1. My accuracy score of training, sorry, the test score is 0.74. This shows you we're probably doing some overfitting. Then I can also check the confusion matrix to get more understanding. But then again, if we want to do something more complicated, and that's something we have not covered yet, but just to show you how easy this is in Python, again, same lines of code, I can just swap my classifier and recalculate everything again. So I just want to show you that although this project might seem daunting to you because you learned quite a lot and you have not a lot of experience, just looking at the exercises that we did yesterday and copy pasting lines of code from there already brings you like already here, because this is, except the lines here with the confusion matrix, all the other bits are actually things that we have already seen before. Just to show you how you can approach this. I hope this was insightful. Now, if there are questions.
Just one question, please. So, to see if I got it right. Essentially, you iterate LR equals and you open something empty, and then you tell it to fit, and you put
Yes.
in your training data and then your testing data.
Yeah. Exactly.
And then you select the methodology, regression, decision trees.
Yeah, exactly. So that's why I was saying the variable LR is a little bit confusing right now, because this was actually saying logistic regression, because maybe this one should have is more clear, right? Because then it's just the model, and then I don't need to specify this anymore. But I think you get the idea. Here, the only thing that really changes in these lines of code is the method here. And besides that, it's basically always the same lines of code.
The function.
Yeah. And that's also what you see here. In my project suggestion, you can see basically the only thing that varies between the iterations is the X model. So basically the technique that you choose, because otherwise it's always the same thing. Create a test split, train the model that you picked, test the model on the validation set, then do a cross validation and experiment with the decision boundary. But all those lines of code are basically independent of the model that you picked. Just to show you that if you start to understand how to do it for maybe linear, so if you in this project you just achieve that you can do it for logistic regression, then you can actually already know that if I know how to do it for logistic regression, then maybe next time I know how to do it for any kind of other model that I know learn about. So just to get some background here, what I now want to do is dive a little bit deeper in what I did. So here, what I did is first train my decision tree. So here you can see I trained a default decision tree. I fit it again on my X train and Y train, which gives me the trait model. And then I can do a default score. The score method, I think, just evaluates the accuracy metric for you. So it's basically doing first a predict and then directly calculating the accuracy metric for you. If you don't want to do this, you can just, for example, calculate the confusion matrix yourself first and calculate the accuracy score. So what we see here is that this is, let me check. So I predicted the train set and I put it in the Y true and the Y predicted, and you see I made 0 mistakes. So what I would assume is that when I calculate the accuracy score, that it should sum my diagonals divided by everything, and it ends up again in 1. So you can see, you can also calculate it easily yourself if you want. But now again, we're only looking at the training scores, of course. That's typically what you do first. More interesting, you want to actually test the model. So now we only do the validation set approach. So what we do, similar lines of code as so the score again is doing the accuracy score for me automatically. And now we see we get a 0.75. Then you see there's quite a big difference between this one from the accuracy score in training and the 0.75 in testing. And of course, we're not just, because you could still argue 0.75 is pretty good. But of course, there are also other things you can calculate. So here I first print the accuracy of my test set. Then I also calculate the precision score, the recall, and something else that I also don't know really what this is about. This is a more complicated KPI that you could also check. And then you can see I have different values for each of the different scores. Of course, we now just fitted the default decision tree. So I now name this a default decision tree model. What I could also do is just specify certain hyperparameters. So I'm now saying never make more than 5 consecutive splits, but I should also never have more than 10. No, I should never have less than 10 data points at the leaf. And now, of course, I want to start comparing those. So here I have some code that's doing cross-validate. The funny thing is that actually there's just a scikit-learn cross-validation method for you, which is pretty straightforward, because what I can just do, I say use a cross-validation of 10. So basically I pass in here 10. I just pass in my whole X and my whole Y. So that is very important that you note that we only use X train and Y X test, that kind of stuff, when we do the validation set approach. Whenever we do cross-validation, you always pass the whole data set to cross-validation, because the cross-validation method is going to make those chunks of data for you. And then it calculates the scores for me. Here, what I also did additionally, because I get 10 scores, what I did, I calculated the mean of the scores and the standard deviation between the scores, just to get a little bit more feeling about the spread. So what you can see here, I did cross-validation for the default decision tree classifier. So you can see I get an accuracy of 0.72 with a standard deviation of 0.02. The precision is 0.64 and the recall is 0.66. Then if you see my tweaked decision tree, I get a similar accuracy, but you can see my precision has increased, but my recall has decreased. Again, depending on your context, you need to pick one of those. You cannot optimize both precision and recall. You need to pick one that you want to improve. Then I'm not going to bother you with the lines of code to calculate an ROC curve, but still I want to show you what I did. So what you can do is you can make this ROC curve for your decision trees to compare them. This looks a little bit weird to you maybe, and it's also a little bit weird because normally you would have a continuous ROC curve for each model. But the issue is with all these decision trees is that even though I tweak them, they are basically going to end up with pure nodes in the end. And for example, this one, and what I mean with pure nodes is that if you end up with a pure node, your prediction probability will be 100%. So if you train your decision tree indefinitely, you will only have pure nodes. So your prediction probability will always be either 0% or 100%. And therefore, it doesn't really matter how you slide your decision boundary. So you will always get the same result. So I basically, this one that I trained basically grow indefinitely. You only have a point at 0, 0 here and 100%, 100%. And that's why you have these, it's not really continuous output that you get from your decision tree. That's just the downside of this simple model. Some other things that you could have done. So feature imports we have not really covered. But what you could have tested is what kind of splits did I make? So, but actually that's probably better if we show that here in the plot figure that I recommended to explore. Here you can actually see that at the top of my decision tree, I did a split on sulfate. And I think the idea is that whenever sulfate is smaller or equal than 333, you go to the left, and otherwise you go to the right. And then you can actually see that we directly did another split. To me, this feels a little bit weird. I don't know why this data set has these kind of weird values, because the next splits are really close together. But yeah, that's just what the algorithm found. But I mean, that's at least something that I would want to look into when I really do this project. And then after that, you will see that you're going to make additional splits. And at some point, you can see you end up with the algorithm stops. And that's probably because I told the algorithm to not grow this leaf any further. Because I don't know if I can see how many values I got. No, unfortunately not. So apparently it wanted to stop here, probably because I told that it could only have 10 leaf nodes. 1, 2, 3, 4, 5, 6, 7, 8, 9, or 9, or whatever. Something like that. So at some point it stops. But for example, if I just change this, so if I would change this to maximum depth of 2, you see that the tree changes significantly. So that's the nice thing about this plot tree. You can just experiment a little bit with this. So for example, what I could also say, min samples, can I have a max leaf nodes, for example? If I have a max leaf nodes of 9, but I specify maximum depth as you can grow indefinitely, then what could happen, I don't know if it's going, oh, I need to add one additional comma. Okay, this is not the result I was hoping for. Maybe if I say 5, let me just get rid of this. Maybe something here is messing me up. So what you can see here, because I specified we shouldn't look at the maximum depth deeper than 4. But if I now say, well, let's look at maximum depth of 8. No, okay, it's still not really interesting. Yeah, and now, yeah, at least what you can see here, and this is actually what I wanted to show, that because I set this maximum depth to indefinitely, you see that this branch gets just a lot of additional splits. And that's something that could result in, for example, overfitting. Then the logistic regression I see there's also a question about it. So I see a question about logistic regression that I said one versus all. And that one is not related to the features, but it is about the classes. So with logistic regression, you can only deal with 2 classes, so either yes or no. So if you have, let's say, 3 classes, you need to do one label versus the rest. So basically, if you have green, yellow, and red, you say green and not green, and then you have yellow and not yellow. But for features, you can have more than 1 or 2 features. So for features here, you can actually see when I train the logistic regression, I just use all the features that are in my X. So I can just specify whatever I want there. Hope that clears it.
Yes, but one question still.
Yeah, sure. Yeah.
So what? So we were running all these like logistic regression predictions, and then you get an accuracy, etc. But I couldn't really find or see what features were then taken into account for this prediction. Is it just all of them?
Yeah. So for logistic regression, if you just this is my code, so it might be more confusing. Let me add 1 line of code. So if I make a logistic regression and I pass my X train and my Y train, then it's going to train on all features.
Yeah. Okay.
So, and you can actually see that by looking at, I don't know, I think it's this one, get parameters. You can actually see, oh no, this is the sorry, this is the wrong one. I always need to check. So here you have the intercept one. So that one is being fit, and then there should also be something like I don't know what the other one is, coefficients. So you will see I get like 9 coefficients.
Yeah.
But what happens if I just I need to check. I don't know from the top of my head all the columns. So for example, if I now just do this and I specify that I only want to have these features, then I still am able to fit. But what happens is, I get a different intercept, but I have only 2 coefficients.
Yeah.
So you control the number of features by passing the columns to the fit method. Yeah.
And then can you see from the coefficient, if you use all the features, you can see from the coefficient which one has the most influence on the predicted value, or?
Not directly, and that's because the unit of measurement of the feature. So if pH is just
normalized.
Exactly, those things are not normalized. So if you want to do that, what you then need to do is first min max scale or something your training set, and then you could do some feature importance. Yeah,
makes sense.
Thank you for your question. All right. So just to wrap up this bit, I use the same lines of code again to do cross-validation with my logistic regression. So I get an accuracy, a precision, and a recall, and those are really, really bad. So something is going wrong here. Also, if I plot my logistic regression in this ROC curve, I see something is definitely going wrong. So I would not recommend using logistic regression for this particular data set, just because it's basically just random. I think, yeah, that's it. I wanted to show you right now on this, on the bits of code that you could have basically done with the knowledge that we have covered. Before we go to the last bit of theory, which is just like 10 minutes of theory, are there any questions that I should cover first?
Not for me.
Okay. Then did I see? No. Okay. Then let's have a look at the last bit of theory, and that is related to ensemble methods or maybe. Yeah, so the last bit of theory, it's really, it's just 10 minutes. Yeah. Because these are basically just very, not so simple extensions, but we are just not really going to add any new mathematics to it. So we're going to talk about bagging, boosting, and random forest. So what is an ensemble method? The idea of an ensemble method is that you're just combining multiple weak learners into one strong learner. So what you have maybe already noticed a little bit when we were doing the coding session together, if you're going to train multiple models, you might end up in the end with maybe 10 different models. Maybe you trained the linear regression one, and you trained a logistic regression one, and you trained one decision tree, but you also made, let's say, 8 variants on top of that. And then, of course, you can consider all these classifiers separately, but what you could also say, yeah, I trained them, so let's just combine them. And the idea here is that, yeah, there's a nice video if you want to learn more on it. And here's just a screenshot of it. So the idea here is that you're going to, in parallel, train multiple different models. I think KNN is, I think it's nearest neighbors or some kind of a neural network. I never know what this abbreviation is. Then here you see someone trained a linear regression. Then there's a decision tree. Then there is a support vector machine, I think. So you have 4 different models. So instead of considering them separately, you could just say, okay, I'm going to train them in parallel, make predictions in parallel, and then I'm going to take the average of those predictions. So average in the sense that if you're doing regression, then it makes sense. If you're doing, for example, classification, then you can do something like a majority vote. And then in the end, the output of the ensemble is just the mean or the majority voting of all those separate models. So it's really not a new method, but more combining things together. Because in the end, if you combine things, then you're less likely to overfit, and you actually are going to lower the error. So that's the idea of an ensemble learner. So nothing really special here. Bagging is also very similar, but in the sense that we're going to train multiple classifiers, or I think typically classifiers or any kind of model. But the idea is, instead of training everything on the same data, which we saw here, because every model here gets the same set of data, we're going to say we're going to consider different subsamples. So each parallel classifier will see a different set of data. So, and that basically means both the different set of rows, but could also be a different set of columns. And that's called also called bootstrap aggregating, and that's why it's called bagging. Again, how do we actually create those sub data sets? So what we do is we're going to draw the data points randomly with replacement, meaning that you could actually end up with the same row or the same record multiple times in a subset. And we're going to draw, and so let's say 10 or 20 data points in each of these subsamples. And then the idea is to train on these subsamples your classifier, and then again combine your parallel classifiers into one prediction. And that's again typically done with a mean or majority voting. One very common example of bagging is a random forest. The idea is that you train your decision trees here at step 2. So at each subset, I'm going to train a new decision tree, and in the end, I'm going to combine all my decision trees together into one single prediction. So again, a random forest is nothing really special. It's just that you train multiple decision trees in parallel, but those decision trees, they see random subsets of the data. And finally, there's one other way to do this. So that's called boosting. Again, boosting, you're going to train multiple classifiers on different subsets of the data, But the idea of the boosting is that we're not going to, and I can actually show that in the next picture, train them in parallel but sequential. So what we're going to do, we're going to first create subsample 1 and then train our model on top of subsample 1, and then we're going to test it. Then with the testing, we know which instances of the training set were not predicted well by this model. And then we're going to say, okay, when I create my new data set, I'm going to give more weight to the ones that I did not predict well, such that the next model is going to learn better how to predict those instances. And then again, I'm going to make a prediction and do some kind of combining the two different predictions using, again, majority voting or the mean. And you can basically, it's not just restricting to 2, but you can make, like, say 100 or 1,000 of these sequential models. Again, just to try to improve the weak learner that you have by training another one that improves on the first one. Visually, you could look at something like this. Suppose you would have, let's say, a classifier that just is a single the single boundary, that on the left you classify it as a blue plus, and on the right you're going to classify it as a red minus. So you can see the first one is really well predicting on the left two pluses, but it's not doing well on these pluses that you see here. Therefore, the next one is going to have give more priority to those 3 pluses that was not fitting well on, and then it comes up with a new boundary. But again, then we make some mistakes here with these three minuses. Again, the next one we're going to give priority to those. And if you would combine these 3 boundaries, you end up with a perfect model. So that's essentially the idea of this boosting. And one very commonly used one is called ABW, and I think you can also use XGBoost. I have to say I have not a lot of experience using those. And actually, that's it about this bit of theory. So it's really not about introducing new mathematical methods. It's more about how do we combine these weaker learners, these simple models, into stronger models. And we do that using some kind of combination of these weaker learners. And one of the famous examples is random forest, where we train multiple decision trees on different subsets of the data. And because of the combination like this, these random forests, so these ensembles or bagging methods are more accurate than the weak learner on its own. And that's it about the theory. Okay. Just checking. I feel like a lot of people feel overwhelmed with this tutorial. So I'm a little bit in doubt whether we should do another coding session, or just that I show you a little bit how to use a random forest. Is there any preference here? Is there still energy in the room to do additional coding sessions, or is everyone exhausted?
I'd quite like to see what you do, but I'm also happy to explore myself. I don't know what the others think, though.
Someone is saying no coding, please. Sure. Okay, I think probably the majority, given all the other messages that I've seen in the chat, we should just look at what I did. Again, we'll not introduce a lot more stuff. Let me see where my coding is. Okay, again, so up to here, I hope everything was kind of clear. So of course, I did not cover all the lines of code to build this ROC curve, but I can just point you to, in the end, there's just this, again, a scikit-learn method that you can use to build the ROC curve. So the nice thing here is that you really don't need to build all these components yourself. So they are already created for you, and that really helps in doing this. I'm just thinking, I'm just going to show you how I did the random forest bit. And then I think I might want to do a live coding session for the remainder of time on how you could also do cross-validation, because I feel like that would be important for most of the people, but I think not a lot of people have touched upon doing cross-validation. So I just want to show you how I would manually do cross-validation. I'm going to freestyle a little bit. I hope that works out in the end, but I can only say that afterwards. Let's look at the bit of code where we left. So here again, we're going to do a random forest classifier. And like before, the funny thing is it's not difficult if you know how to do it for any other kind of method, because in the end, it's just, again, the same lines of code to train your random forest classifier. And then again, it's again just doing a predict to make predictions on, for example, also scoring. Let me just do a score of my X test and Y test.
Sorry,
Just,
David.
yeah.
Would you? Are you supposed to be sharing the screen?
I'm not sharing the screen. Oh, I'm really sorry about that. Yeah.
Okay.
Somehow
Just checking. No
I
problem.
lost. So again, let me just first show you what I wanted to say here is I was going to say all these things like cross-validation, making predictions, training the model, scoring, everything. Basically, everything is built in scikit-learn. So you don't need to worry about that if you don't want to. So I'm not going to dive into all the code that I created myself to do the ROC curves of scoring. So you just need to assume that I did that correctly. And of course, there might be mistakes in there. But if you're interested to create your own ROC curve in the end, if you still want to continue with this in your own project later on, just look at the scikit-learn default methods that help you already a lot. And that's why I was saying there is also a cross-validate method that does cross-validation for you directly. So I think in the remainder of the time, it might be worth checking if I can do this manually, just to show you what is typically required if you want to do a cross-validation yourself. So more or less give you a feeling what is happening inside this cross-validation method. For now, we're just going to check the random forest classifier. And again, I want to show you how easy it is to train it, if you know how to train any other kind of model with scikit-learn. So here you can see you make, again, a random forest classifier instance. There's a lot of random stuff going on in this algorithm. So always specify random state, because otherwise you're not going to get the same classifier every time. And again, we pass our train and train data to the fit method. And if you're interested to get the score, then the accuracy, we can just do rf.score, or what we can do is pred is the prediction here. And then add one more line of code to do, for example, accuracy score of y true is y true. I think what is y test. And here you can, again, ypred is the one that I just calculated. So here you can see, of course, you don't need to specify this. So here you can see it's the same one. I think this is the same value that you get out of just the normal score methods. Let me just validate all at once. All right, of course, I need to specify y test. So you can see by default, the score here is the accuracy metric. And then, of course, if you're interested in something else, you can just swap this with another metric, and now you get a different one. And of course, depending on your own context, you want to pick the accuracy, precision, or something else. So again, what I want to do here, there are also different things that you can specify on the random forest classifier. So what you can specify here is how many random decision trees you want to train in parallel. So this is 250. And what you can say, you can of course also of each of these decision trees specify how they should be trained. So on each decision tree, I'm now going to say maximum depth is 10. However, you could argue that you don't need to do this because you're training 250 decision trees in parallel. All the hyperparameters on the decision trees are going to not matter a lot. And you will see that if you train, do it yourselves. So here I'm going to train a default random forest and my tweaked one. And what I can do is, again, do cross-validation using the cross-validate method. And what you can already see here is that it's taking a very long time just to do cross-validation of my default so random forest classifier. And that's because I need to 10 times train 250 decision trees in parallel. So that will take a lot more time. Even the one that I tweaked, I think this is going to take a little bit more. That was the downside of this thing, so I'm going to already do it. So as you can see, this can take really like a long time. This was already taking 40 seconds, while I think a decision tree, you can typically just fit that in a couple of seconds. Let's just wait a little bit before this line of code is done, and I'm just checking if there are any other things to mark down. I know are a bit of running. Can we get the recordings? Okay, yeah, that's nothing I need to worry about right now. All right, so in the end, you could have built something like this. So you can see the green and the orange one are my decision trees. The black one is my logistic regression. The blue one is the random no value classifier. And then here I have my red and my purple random forest classifiers. And you can already see which one is the default one. The red one has basically a similar performance as the purple one. So you can spend a lot of time in tweaking this, but just because you are going to fit so many independent weak classifiers, it doesn't really matter. But still, it's always a best practice to get those last bits of additional performance out of it if possible. So based on this, I would probably say you would want to go for something like a random forest to do this project, because that one has the highest performance. But again, if you want to explain to the people that need to drink the water that you make the predictions on, then you probably want to use the decision tree, because if you have the decision tree, you could also just hand out your printed plot tree version, and then based on their own field measurements, they could decide whether this water is potable or not. So again, based on whatever kind of context you're working in, it really depends which one you want to choose. Any questions on this bit of no? Then I think with 50 minutes left, if there are no questions, then I can just show you how to do cross-validation manually. But before that, I actually want to check, are there people interested in doing cross-validation manually together?
Yes.
Okay, cool. One yes is, I think, already enough, I hope. Just seeing, okay, I see multiple yeses and ox, so that's let's do that. Let's see where I want to put that bit of code. I guess I can do it here. So I'm not going to do everything myself, because that would take a lot of time. What I don't want to do myself is create the chunks of data. So there's this k-fold for me that's provides train test, and this is to split data. Yeah, so what you can use this k-fold method for is give you a set of indices to use for test and training. So let me show you how you can use that. So KF is like the k-fold. I think I've imported that one. Yeah. And we want to do n splits equal to 10. And then I think you need to do something. Let's look at it. So this is also just nice to show you how I do this kind of projects, because I also don't know all these methods by heart. So I spend a lot of time just reading the documentation of the scikit-learn and looking at examples, because those are typically the ones that really help. So this helps me to see if I want to use this. Okay, I typically probably also want to specify my random state. But if I want to do this, I need to do this kind of for loop. So I hope you're familiar with the Python for loop. So I'm going to do random state something, some random number. Setting a random state has no effect since shuffle is false. Okay. Then I say shuffle is true. So what this function will provide me with is basically, let me just print replication I, and then print test index. So just to show you, in each of my iterations in this for loop, I get a certain index set passed from this k-fold. And what I can do now is use this index to get my test and train data. So instead of just doing one, let me see if I can just bring up again the picture one more time, what we're actually doing with k-fold cross-validation. This one, and then let's go here. So in the end, with k-fold cross-validation, we wanted to do this. So in this case, I picked k is 10, so I will get 10 of these actually. And what I want to do in each for loop is I get a set of test indices, which is actually this orange bit, and I get a set of train indices, which is this blue bit. So what I need to do next, since I now have my indices, get my training data x train in my cross validation. I just want to give it a different name. So what I need to do is x, I think it's called, I need to check that for sure, but I think I can do something like this, basically saying I want to just have these indices from my x. So I think if I now do x train cv.head, yeah, so now you can see using this line of code, I get a subset of my data at each replication. And of course, I need more, because I also need my targets, because otherwise I'm not able to train. I can do the same thing, I think, here. Train index. Yeah, that's allowed to do. So now I get my training data, but of course, within cross-validation, I also want to test. So I do the same lines of code, but then with my test indices. Y test is y.ilog test index. So now I have my train and my test indices available within each of these replications that I'm doing here, because I've written the code inside this for loop. So what I want to do here is, of course, now I have my train data. What I want to do is train my model. So in this case, let's just train a random forest. So my model is a random forest classifier. I'm just going to and estimators that it's not going to take a very long time. Let's say 50. I'm going to train 50 decision trees. And let's set again a random state. So here, this is the bit, of course, again, to train the model. Here I'm going to now, of course, train on the cross-validation chunks that I created. Again, note that I passed in the whole data set here. And now, because I have trained my model, what I want to do is test it. So for now, let's just do, for example, accuracy, because that's the easiest one. Maybe I can actually also calculate that manually. No, I don't have enough time for that. So what we do here is we do a model.predict of X test, Y prediction inside my cross validation. And what I'm now going to do is calculate the accuracy score. So score in my CV is accuracy score of my Y true is Y, and I have to be very careful, Y test CV, and then my Y predictions are the ones that I just predicted. One important thing here, what I want to do is, because I'm going to get more than one score, I want to actually somewhere store my scores and add them after each iteration. So I'm going to say scores up, add a new score, and that's just the one that I just calculated. And actually, this is, I think, everything that we should need. Let's hope that it works in one go. Looks fine. So now you get your 10 scores, so we can actually test that here. So you can see I get pretty different results even. So you get actually a maximum of 0.82 accuracy and a minimum of 0.75. So this will have impact on your scores. Then, and that's of course also the final bit that we discussed at the start of today, we need one more step, and that is aggregating the scores. And I think that's just now done with a mean. So I can do np.mean. So there's a NumPy. NumPy is a very useful library with all these kind of mathematical operations that you want to do. So this one is for me now just taking the mean of the scores. So I get a mean of 0.79. And that's basically it to do cross-validation manually. And of course, if you really want to do it manually, you might want to do splits. In certain cases, that is actually something you want to do. Let me give you one example there. At some point, I created anomaly detection models for valves in pipelines. And a typical chemical refinery can have, let's say, 100,000 valves, and each valve needs to have their own trained model. And you typically have 1,000 features available for each valve. So you also want to test multiple feature sets for the model. And in the end, the idea was that I built a classifier that could automatically identify which of the, let's say, 10 models they trained for a certain valve was the best one and which should be used in practice. So I got a large data set of, let's say, 100 models, and those models were of a specific chemical refinery. So I think I had like 5 chemical refineries, and each of them had like 20 valves in there, and then each valve had around 10 models. What you would, if you're doing it like this, you're just going to get a random split. So what ends up in my test set is just a random shuffle, and so I get all the different refineries will end up in my test set. What would actually be more interesting in this case, because I have 5 refineries, is say I'm going to do a cross validation of 5, and every time I'm just going to set aside all models that are trained for one refinery, because that is actually how I'm going to use this in practice. I'm going to use this in practice by having it trained on the refineries that I already know. And the second I'm going to add a new refinery, I need to, of course, rerun or use this model that I made to identify the models that are good, yes or no. So in that way, I get a more fair evaluation of my model in practice. So in certain cases, just the automatic split will not suffice. But again, that depends on the context that you want. In this case, I don't think it does really matters because we just have water. So you can do random splits. I hope this was one useful bit of coding together. Maybe that's something for the person that's going to do this next time, is have more coding sessions together. The only downside of that is that I think you only learn this by doing it yourself. And seeing me doing it is of course nice, but doing it yourself next time is something else. Hopefully, you all learned a little bit about this. At least you learned a little bit how to get it started, and hopefully that's already enough for you to get out of this course. I really enjoyed giving the course. I hope, although there are definitely some concerns I hope you also enjoyed the content, enjoyed the exercises, and I hope this was valuable knowledge for your project during this fellowship. So good luck with your project, and enjoy your evening. Before I really close off, are there any other questions, by the way? Otherwise, we can close for today.
I was going to ask you.
Of course. No, go ahead.
The basic steps you mentioned, because I think those are the most crucial takeaway from the session. Are they available on GitHub? Those crucial steps to building a model with Python, be it regression, be it decision trees.
Yeah. So this project suggestions that I've written down, I'm not sure.
Yes, the project suggestions.
Yeah.
Yes.
So these are just in the README. If you go to the classifier project, there's this README file, and you can actually already see it directly here. So yes, these are in the.
Okay, brilliant, brilliant. Yeah. Okay, brilliant.
Cool.
Thank you.
Thank you so much, David.
Yes, then I think we can close for today. Thank you all for your attention and your participation, and good luck with your own projects.
Thanks a lot.